Hello everyone, I'm Daniel Armbruster, and I'm going to be doing my presentation on control flow integrity and bending. So, we've been spending a fair amount of time in this class focused on memory corruption exploits. These are things like the buffer overflow vulnerability or the format string vulnerability. With these exploits, we've been trying to essentially overwrite some bit of data to try and get the control flow of the program to be what we want it to be. Potentially, or to leak information, particularly with the format string, but we're focused primarily on corrupting the memory. And that the defenses that we've been focusing on for this have typically been prevent the exploit defenses. This is opposed to prevent the corruption, which we haven't really touched upon, and it isn't really relevant to what I'm talking about, since control flow integrity also focuses on prevent the exploit. But just as a brief summarize, prevent the corruption would simply be preventing the memory corruption that we're talking about in the first place. Things like ASLR, non-executable stack, or stack guard don't prevent the corruption. They simply attempt to prevent the program from doing anything malicious once corruption has been detected. Control flow integrity, likewise, is another means of preventing the exploit. It doesn't prevent the corruption, but the idea is it wants to constrain the program in some way, such that if this constraint is broken, then the program will crash or no longer work. And particularly because it's control flow integrity, it's focused a lot on preventing control flow hijacking. And so in this sense, ensuring that whatever branches the program follows, wherever it goes, whatever functions it calls, it always does this in a way that's allowed, that can at least on the face of it be benign, or at least could be conceivably benign. So to get into what control flow integrity is, it's also important to understand what a control flow graph is. Now, control flow integrity is, once again, a security countermeasure that's prevent the exploit, and it's stateless. Not by stateless do I mean agnostic to the particular program, but through the running of the program, not particular about what state the program is at that time. And it does this by enforcing what's known as a control flow graph, which you can tell by this image on the right, which is essentially just a finite state machine. Whenever the program is compiled, there's some procedure, some algorithm that's done to generate this kind of graph and be able to say at any particular point, at any particular node, in any particular function, these are the places where the program is allowed to go and nothing outside of that. So, by having that restriction, it's like the other countermeasures, where it's another restriction that makes it more difficult to, in some sense, break out of and do something malicious, such as, if you're in a string copy function, you shouldn't be able to call a shell, is kind of the general idea behind it. You shouldn't be able to do something, that's way out of the ballpark of whatever your current function is. And it implements this, or one of the ways to implement it that was strongly suggested, was with a shadow stack, which, as we all know, there's a stack on the, I'm pausing here. There's a stack on the, that all the data goes on, and that on that stack there are particular return addresses. A shadow stack is like that, but instead of having all the other data and having all the other data written to it, it only contains the return addresses, and that's what I was getting stuck on. And in that way, if you have some data that's being written to a buffer on the stack, you can't override the shadow stack, even if the return address on the main stack becomes corrupted. And so in order to deal with that, or in order to manage it appropriately, the shadow stack needs to be stored separately. This does come with a performance detriment. It does harm the overall performance of the program. But the idea is it's a way of making sure that whenever we access the return addresses, that we can use it to implement a CFG and make sure we're only going to the locations that we should, and also make sure that whenever we return from a function, we can compare the return address that's on the main stack and the return address that's on the shadow stack. And if they differ, we know that there's been some corruption going on. So this is the general way of implementing a CFG, or some approaches to implementing a CFG, although others exist. But once we have a CFG, how do we evaluate its accuracy? And here we'll have terms like coarse versus fine versus fully precise. Coarse versus fine is relative and it doesn't have a strong definition. Fully precise, which I'll get into in a slide or two, does have a strong definition. And then it's also important to note what this scheme does and does not do. And one of the things that it doesn't do is it isn't effective against exploits that do not alter control flow. So, if there is an example of this might be if there is a call to an exec function, right, where you rewrite the program memory and basically make it a new program, uh, if you change the argument of that, because this doesn't prevent overwriting data on the stack, if you change the arguments to that function call, this isn't going to do anything for you, right? Because you're already going to go to exec, and so that it's still on the control flow graph. So it's still allowed. So there are some ways in which this approach doesn't really help you. So moving on, to get more into the particular terms and how to differentiate CFIs, fully precise is the only one that's rigorously defined, and that's a branch that goes from one instruction to another is allowed if and only if there is also, or this is the only, benign instruction that makes the same control flow transfer. So the idea basically being you can only do something if it is possible to have done that and for it to have been benign, is kind of the idea behind it. We don't know how to achieve this standard. And on the previous slide, it had mentioned this, but we can only ever over approximate. We can't, we suffer from an issue where we're going to have more edges than what we need. And more edges, it means it's going to be less secure, meaning it's less effective as a security countermeasure. So it's one of the things that we have to balance and understand about this. So the particular sources of over-approximation can be that from any particular node, we don't need to call everything that might be there or that might be possible, but we still might have them in the graph. And so having those extra outgoing edges is a problem. The other is that some nodes of the graph that might be better being more granular could be merged together and be larger chunks. And the issue with that is it eliminates transfers, the security check of transfers inside of those combined nodes, those collapsed nodes, as well as allowing if two nodes have different outgoing edges except they're linked and then they merge, then they become a superset, the combination or the union, I'm sorry, of those two edges. And so in that case, there's an issue where one node is going to have edges outgoing that it only has because it merged, and it's only because it was able to connect to this other thing. So those are issues where it's over approximate and we don't know how to get fully precise CFIs and CFGs. But there's also the issue that even if it is fully precise, it isn't a guarantee of protection. Like with the exec example system call I was referencing earlier, if they are fully precise, that's still an issue. If it doesn't alter control flow, or if it stays within the control flow allowed, you can still have exploits. So that's also an issue to be concerned with. And so the particular kind of attack where a CFI, where we still follow the CFG, and so we do not violate the integrity, is that is known as a control flow bending, where even if the particular stack trace, the execution trace, does not match what is a possible valid one, as long as it's still within the graph, CFI isn't going to catch it. And so any attack that is able to stay within the graph and is able to do something malicious, even if its execution trace isn't possible in the intended route, would be a CFB. And so some examples of this are, once again, changing the arguments to a function call that has important differences in what happens, like with exec. Changing a flag like is admin, which is kind of like going down a different path in the CFG, but it isn't breaking out of the CFG. But because going down that path allows a potential malicious action, it's still something that should be concerning. And likewise, changing a function pointer to another function, as long as that function's in the CFG, it's still allowed. But not intended, and so it's a control flow bending. So with this possible attack and the security countermeasure, it's important to develop a threat model for how this could be accomplished, how this attack could be accomplished. And one of the things that we have to, and the thing is, CFI is a pretty general thing. It can apply to most programs, and it, or probably all programs. And it isn't really against anything in particular. It's just trying to be restrictive in a way that hopefully, and quite possibly, is a good idea. But, and so in order to imagine a potential attacker in this context, we assume that they can write arbitrarily to memory at one point in time, but that they can write anywhere that's data. They can't write to code, code stays the same, and the data is non-executable. But because this is so general, we need to allow our attacker to be able to be general, being that there is some time at which they can change the data. But we can't really guarantee whether or not they can only attack specific parts or if they could attack other specific parts, because those kinds of constraints aren't reliable as to where they can write in data, even if they are usually true. And given that this is a general defense, we have to understand it as a kind of, we have to understand our threat as a kind of general threat. As well as attacker goals being arbitrary code execution, where they're able to do anything in the context of the program and are able to execute whatever they want and call whatever system calls they want and be able to do that with the full permissions of the program. Confined code execution, where they're able to do anything within the address space of the program, but maybe are not able to do everything with all of the system calls, or able to use all of the system calls available to the program. And then the weakest attack, or the easiest attack, I guess you could say, is information leakage, where we simply allow certain values or certain data to be given to the attacker, or made available to the attacker. So then, given the CFIs and given the CFGs, how do we understand how good a CFI is, or how effective it is? And some of the terms that I mentioned earlier were, we can describe it as coarse versus fine. A coarse CFI is one that has a poorer approximation of the fully precise CFI than the fine does. And how do we differentiate these two? How are we able to say whether or not one is a coarser or a finer CFI compared to another? And we have some metrics that we're able to do this with. Average indirect target reduction, which is essentially the amount of percent of indirect branches that have been pruned in creating this CFG. And that the higher the percentages, the more branches that we have pruned, the finer of a CFG we're dealing with. And likewise, we have a similar thing with gadget reductions, which we were familiar with the RETs to libc and RET to RET labs, where essentially what we were doing is just seeing where in the code, if we could control where the return pointer goes to, where in the code we're able to, where in the code we're able to prevent them from going to places where we're able to do some useful instruction and then go to a return statement and prevent those kinds of things, lower the number of gadgets available, right? Which is that do some assembly instruction and then return. And then there was an alternate that was proposed, which doesn't really define between coarse versus fine, and it isn't really meaningful for that, but it is useful. It's kind of a basic test, but it is a useful one. And that's the basic exploit test, or BET is how I'll refer to it. But it essentially aims to show whether or not a CFI is trivially broken. It doesn't guarantee security, but it does help to say that, do we get anything from a CFI? And the next example I'll give will illustrate that, where given a broken program, does the CFI really help at all? So the thing is, and once again, I'll elaborate on this more, but these metrics are somewhat ineffective. The first two help in the kind of theoretical approach, but they don't actually necessarily indicate whether or not there's a vulnerability. They just indicate whether or not we're closer or further from a fine closer or further from the fully precise CFG. And the basic exploit test doesn't necessarily indicate whether or not it's secure, just whether or not we get anything from it. So to move into practice and to see how something like the basic exploit test works, we can apply a CFI to what's a trivially broken program. And to just go through the program really quickly and help illustrate what's wrong with it, if you look at the second function that's defined, the vuln func function, we see that we have a character array of 1024, but we see that the read system call, it goes up to 2048. So obviously the read can write to the buffer more than what's there. So obviously there's a buffer overflow. And so when this this obviously vulnerable program was ran, we were able to see that there was what looked like, although it's relative, what looked like good metrics like error and like gadget reduction, but there still existed a number of gadgets where which were in libc, which together were allowed arbitrary system calls, and that was allowed to gain arbitrary code execution on the platform. So, and this is a practical CFI. It isn't even the fully precise one. And so we have to consider that, at least for what's trivially broken programs, the CFI doesn't necessarily offer protection. So it's kind of a mark against it, or at least a sense that it can be difficult to see what you get, even though it does have an intuitive appeal, in the sense that it forces a constraint on the program that maybe an attacker would not like. And that leads into what my thoughts on the CFI are, is that it's general, it's powerful, but it isn't necessarily effective. It's powerful, I guess, more portable. It suffers from being a bit of a heuristic. It could be useful, but it is very general. And it may be worth considering if it were possible to generate a fully precise CFI, although that too likely would not give us a guaranteed benefit. It kind of makes me think of ASLR in that sense, where ASLR doesn't prevent us from doing anything, it just makes it a lot more annoying to do anything. Right, and that isn't, but it doesn't prevent the exploit, it just makes the exploit more difficult, but not, but even then, potentially not substantially so. Part of it too may be that while 99% error reduction and 98% gadget reduction may look effective, maybe the metrics for making them truly effective are actually much higher than that. But there is also the consideration that even if they are arbitrarily high metrics, that if there is just one set of gadgets, even if there is one set of branches, that even at the highest possible metrics for error and gadget reduction are achieved, if those still allow a vulnerability, then our function hasn't done anything, right? We have that issue to contend with, where we simply have to acknowledge the fact that that these metrics may not be useful at all if the exploit is still allowed, as long as, no matter how high those values are. And so it, in that sense, it kind of strikes me as potentially ineffective, or at least not really something that can be relied upon. It really strikes me as a general kind of application. But that may also be an issue with the kind of general form prevent the exploit as opposed to prevent the corruption defenses that we're seeing. That because they already, as it were, let the enemy into the front gate, then there's a kind of thing where you're kind of playing catch up no matter what you do. You're kind of having to be very reactive and presume what the attacker is going to do. I'm not terribly familiar with prevent the exploit countermeasures, but it just strikes me that if you're able to prevent the corruption countermeasures, it strikes me if you're able to prevent corruption in the first place, that should be just generally more secure because there's just less to think about in terms of all of the ways that it might go wrong. But it's so then moving in to the question I have for you all, and I'm almost over time, and I'm sorry about that, but there is an intuitive appeal to CFIs, given how it enforces what we want the program to do anyways, and only requires a very general understanding of both the program we're working in and the attacker. Ideally, this allows for robust and portable defenses, but can suffer from being so general as to not add substantially to the security. And given this kind of thinking, do you think that this general approach to cybersecurity, one that makes a general model of an attacker as opposed to specific vulnerabilities and tries to defend against that, rather than more program and platform specific approaches, hold any promise? And why or why not? That is it for me. I think I'm a little over time. I'm sorry about that. And I hope I had a good question and it sparks discussion.